Okay, thank you. Thank you for the nice introduction. And also I wish to thank to the organizing committee for this nice conference. My research focus on module ring theory and homological algebra. And my talk will be on purities relative to some class of finite presented modules. And the notion of purity plays a significant role in module and ring theory. And there are and there are several generalizations of purity since it was presented in the literature. And the most common one is introduced and studied by Warfield as follows. An exact sequence 0, A, B, C, 0 of right-arm modules is called C-pure for any class of right-arm module C if hom SB, hom SC is an epimorphism for each S from the class of C. And if C is the class of all finitely presented right-arm modules, then we have the notion of Cohn's purity, and this is also studied by Warfield. And if we restrict ourselves to this class of finitely presented modules, these are factors of finitely generated free modules with cyclic modules, okay? And if C is this class, then we have the notion of I purity, and this is also studied by Knott. And if C is the class of cyclically presented modules, then we have the notion of RD purity, and also this is studied by Warfield. And naturally, we have purity implies I purity, and I purity implies RD purity, but not conversely. And also, it is natural to consider the injective and projective objects of these purities. And Warfield, in general context, defined as a module as C-pure injective in case A has injective property with respect to C-pure exact sequences. And C-pure projectivity means it has projective property with respect to C-pure exact sequences. This is true for any class of modules. So if C is the class of all finitely presented modules, then we have pure injective and pure projective modules. And this is also studied extensively by Warfield. And also if we restrict ourselves to this class of finitely presented modules, these are the quotients of finitely generated free modules with cyclic modules, okay? Then we have I pure injectives and I pure projective modules in this context. And it is also studied extensively on that paper with Berbody and his friends. So if C is the class of cyclically presented modules, then we have the notion of RD injective and RD projective modules, and it is also studied by Couchot extensively. So in the following papers, I purity, I pure projectivity, and I pure injectivity are studied extensively. And motivating by the purity and RD purity, we continue the study and investigation of the I pure projective and I pure injective modules and their homological objects. So it's clear that projective modules are I pure projective, but the converse need not be true. If we consider the ring R as Z over P square Z for some prime integer P, then here R over PR is I pure projective modules, since it is finitely presented here with cyclic quotient. Whereas the module R over PR is not projective, otherwise this epimorphism must cyclize. But we know that it does not cyclize. So the converse is not true here for A. And also injective modules are I pure injective, and also the converse need not be true if you consider the Z module M as a Z over PZ for some prime integer P, then here M is I pure injective Z module, while it is not an injective Z module. Okay. And also another natural question, we said that purity implies I purity, but the converse need not be true. If, for example, Brewer and Costa studied on that paper the following example, this is a really nice and constructive example. Here R is a polynomial ring with two variables. Sorry, here R is a polynomial ring with two variables with the quotient, with this quotient. Okay, and S is the polynomial ring with one variable, but here with small x and defined by this small x and small y. Okay, so here these constructive examples R is I pure in S, but they prove that on that paper R is not pure in S. Okay, so this is so by using this example also we know that every I pure projective modules are pure projective, and also I pure injectives are pure injective. But the converses are not true. Also, we will use this example to say that the converses are not true. So here, Brewer and Costa on that paper prove that here the ring R is Artinian. So it is well known that every Artinian module is pure injective. Okay, hence the Artinian ring R on that example is pure injective. Okay, but R is not I pure injective because since this map is pure but not splits. Okay, so also on that paper the authors prove that every right arm module can be embedded as an I pure submodule of an I pure injective module, and every module A, for every module A, there exists an I pure epimorphism F with P I pure projective. Okay, so these two lemmas, by using these two lemmas, we observe that every right arm module has an I pure injective envelope, and every right arm module has an I pure projective precover. Okay, so by using this remark, we can say that since every right arm module has an I pure projective precover, we can say that A has a left I pure projective resolution. Okay, so this means that there is an I pure exact sequence with each PI is I pure projective. And so obviously these complexes are exact since projective modules are I pure projective. So by an X and I, we will denote nth right functor of Hom with respect to the class of all I pure projective modules. And for two modules A and B, XNIBA can be computed using a left I pure projective solution of B. So the left I pure projective dimension of A will be denoted by IPDA, is defined as infimum of the I pure projective resolutions of A. Okay, so if no such an exists, we will set I pure projective dimension of A as infinite. And the global left I pure projective dimension of M will be denoted by global IPDR. This is the supplement IPDA, I pure projective dimension of A for any right arm module A. Okay, so in this step, it is important to understand this dimension idea. So the first question is we consider as a first question, can we say that XI0 BA is isomorphic to BA, Hom BA? Yes, it is isomorphic, and also it is isomorphic to X0 BA for all right arm modules A and B. And but if n is 1, it is not isomorphic. We have only monic map from X1 IBA to X1 BA. This is monic. So it is natural to consider when the second statement will be isomorphism. If R is polynomial regular, here I pure projectives are projective and I pure injectives are injective. So the second statement of the proposition is an isomorphism. And if we replace one with arbitrary n, also this map will be isomorphism. Okay. So another result for a right arm module A, I pure projective dimension of A is less than or equal to n is equivalent to the following conditions: xi n plus gab is 0 for all b, and g bigger than equal to 1, and xin plus 1 ab is 0 for all b, and every nth I pure projective syzygy of A is I pure projective. Okay, and for a ring R, global I pure projective dimension of R is less than and equal to n is equivalent to following conditions. Okay, so if R is a von Neumann regular ring, then the dimension of R is equal to global I pure projective dimension of R. And if global I pure projective dimension of R is 0, then dimension of R is equal to the weak dimension of R. And in general, we have that dimension of R is less than and equal to global I pure projective dimension of R plus weak dimension of R. Okay, and we have the following theorem. If we replace n with 1, we have the global I pure projective dimension of R is less than and equal to 1, equivalent to the fact that this is equivalent to the fact that I pure projective modules is closed under I pure submodules, and this is also equivalent to the fact that I pure injective modules are closed under I pure quotients, and these two X conditions also are satisfied. And if we consider the ring with global I pure projective dimension of R0, then this will be equivalent to the fact that every module is I pure projective and every module is I pure injective, and the following X conditions. Okay, and moreover, if R is a commutative ring, the rings with global I pure projective dimension of 0 will be equivalent to the Kötter ring. Okay, by a Kötter ring, we mean that each R module is a direct sum of cyclic modules. Okay, this is my last result, and the following are my references. Thank you for your attention.
Thank you.
If you have any question, I can try to explain.
Okay, are there any questions? We have time for one question.